Um, Another example here. This is another kind of not like a testable type of example, more kind of a thought exercise, kind of, I guess. A national chain of SAT preparation schools wants to know if using a smartphone app in addition to their regular program will help increase student scores more than just using the regular program alone. On average, students in their regular program increase their scores by 128 points during a 3-month class. To investigate using the smartphone app, they have 5,000 students use the app along with the regular course and measure their improvement. They will test the following hypothesis: that the mean is equal to 128, so there's been no change since implementing the iPad or the smartphone app, versus the mean is now greater than 128, so the smartphone app improves scores, where mu is a true mean improvement in SAT scores for the school. Where mu is the true mean improvement for SAT scores for students using the smartphone app and class. I think that should have been worded a little better. My apologies. After 3 months, the average improvement was 130. So the program by itself gave you 128 point increase. Looks like the sample gave you 130 point increase. So there is some evidence that this smartphone app is effective, more effective, right? But 128 to 130, that's not a big improvement. So, and the standard deviation is 65. So do you think that's a significant improvement? I'm thinking you might say no, but what you might be missing is that you surveyed you experimented with 5,000 kids. This is a huge sample size. Big sample size, lots of power. So we might be able to detect just a 2-point difference on this SAT improvement score. Without running all the steps, find the p-value. So let's just use our calculator to get that p-value real quick here. Yeah. Menu, come on. Menu, statistics, stat tests. So this is a one sample t-test. So I got the statistics, not the raw data, so put in the stats. I'm hypothesizing it's 128. My sample was 130. Sample size was 65. Surveyed 5,000 people. I want to know if there's an improvement in my scores. P-value is 0.015. So although the increase was really, really, really minor, I do have enough power to detect a significant difference because my sample size is so big. So I will reject the null and conclude that the scores are now, the app helped. Were the results practically significant? So the idea here is that we had statistically significant results. However, is this a practical significance? I think the SAT is like, 1,600 points or something. This is, instead of an improvement of 128, we're getting an improvement of 130. That's really not that big of an improvement. Perhaps not a big enough improvement to implement some kind of smartphone app, invest in that, expect the kids to have it, retrain teachers. So the question is, yes, we have a statistically significant difference, but we don't really have a practical difference. So I guess this is just some significance test wisdom. Just because you have a statistical significance doesn't always mean you have a practical significance. So just be mindful. So we got a little joke here. Jelly beans cause acne. Okay, so she's making a claim. So this guy's saying scientists need to investigate. However, the scientists are playing Minecraft. Whatever. So the scientists say we found no link between jelly beans and acne. The p-value was greater than 0.05. So it looks like they're running their test at an alpha level of 0.5. Well, that settles that. Then the troublemaker girl here says, well, I heard it's only certain colors that cause acne. So he's like, scientists, we need more testing. but they're playing Minecraft. So they test purple, no. No Lincoln brown, pink, blue, teal, salmon, red, turquoise, yada, yada, yada. No, no, no. And right here, I should put it in green, because it says they found a link between green jelly beans and acne. The p-value is less than 0.05. And they say, whoa. Color, 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 color. No, 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 no. So it looks like they do 1, 2, 3, 4, 5, 1, 2, 3, 4. So it looks like they ran 20 tests. 20 different significance tests. And they found a significance on one of them. So they publish in the paper, green jelly beans cause acne, 95% confidence, only a 5% chance that something like that would happen just due to random chance. So, do you think green jelly beans really do cause acne? And did they scientifically prove it? Well, it's not a coincidence that they ran exactly 20 tests. If we assume that jelly beans don't cause acne, then a type 1 error would be rejecting the null when the null is true, meaning the jelly beans don't really cause acne, but I mistakenly say they do. So that's probably what's happening here, right? Maybe. The idea here is that you're running 20 tests. The probability of committing a type 1 error is alpha. 5% is 1 time out of 20. So on average, you would expect to commit a type 1 error 1 time in every 20 tests. We ran exactly 20 tests, so it didn't seem so unusual that we would reject and commit a type 1 error in one of them. So this kind of brings to light a bit of an issue in statistics. If you run multiple tests at an alpha level of 0.5, the probability you make a type 1 error in at least one of them is going to be much higher than 0.05. So let's just do this example here to kind of illustrate this idea. Suppose you run 20 significance tests in each case where the null hypothesis was true. Find the probability that we commit a type 1. So probability of a type 1 error in one test is 5%. Assuming we're running it should have said that we're going to run it at an alpha level of 0.5. So what's the probability we commit at least one type 1 error in 20 tests? If you remember from your probability, at least one kind of leads you to that rule of complements. So this is going to be 1. This is going to be 1 minus a probability. What's the complement of getting at least one error? Well, at least one error would be 1 error, 2 error, 3 error, 4 error, all the way up to 20 errors. The complement would be no errors. So that's 1 minus the probability of the first test you don't get a type 1 error is going to be the complement of 5%. I think we do need to assume that we have independent tests. If the tests are independent, then the probability of the second one would be another 0.95, on and on and on, and there would be exactly 20 of them. You got to get 20 no type 1 errors. So we can type that in our calculator. 1 minus 0.95 to the 20th power, 64%. So is it unusual that we would get one or more type 1 errors? Well, no. It happens in actually over half. If you run 20 tests, 64% of the time, you're going to get at least one and maybe even more than one type 1 error in at least one of those tests. So this is way too high, or perhaps. So this is a little bit of a BAPS problem here, a little beyond AP Stats, but if you're running multiple tests, what you can do is you can actually adjust the alpha level lower this alpha level so it's not being run at 0.5, so that your overall chance of getting at least one type error, so that this becomes 0.05. So we can just kind of set up this equation. 1 minus, this is 1 minus alpha to the 20th power. If I want my overall error rate to be 5%, then what do I need to pick for this alpha value in order to make that happen? So I'm just going to solve this equation, and I'm not going to solve it by hand. I'm just going to use a calculator because why not? So 1 minus, parenthesis, 1 minus, I'm going to put an A in to the 20th. And I want that to equal 0.05. I want to solve it for A. So we're getting multiple solutions because you got an even powered polynomial here, I think, and if you expand that all out, right? So obviously this 199% isn't going to work, but this is 0.0026. 0.0026. So what this means is, if you want to have an overall alpha rate of getting a type 1 error in 20 tests of 0.5, then you should run each individual test at a 0.0026 level. Then the probability that you get at least one type 1 error in one of those 20 tests is going to be 5%. What you really should just know is that when you run multiple tests, it increases the probability of making a type 1 error. This happens in the statistics world, right? You're trying to get a drug approved through the FDA to put this drug on the market. So you do a trial, you do a test, and you get a p-value of 0.08. So then you say, well, gosh, that's not low enough. So let's run another test. Let's keep running our tests until we get significant results. Well, if you always run them at alpha value of 0.05, you're going to have some problems, I guess. Okay? Now, this last problem is another BAPS problem. This is how you actually calculate the power. If you're interested, you can put in this URL and see a video of this solution. I'll maybe even try to dig up that solution, that video, and attach it to these notes so you can see it. But that concludes chapter 9.